Tonight is August the 27th, 2022, and I've got an interesting project going on right now. I've spent a lot of time on it, and I think I'm getting somewhere. My dear friends here in El Paso have inspired me to continue this, and what I'm going to do is I've gotten back into astronomy, but this time radio astronomy. And what I'm going to do, I'll tell you the unique part of it in just a second. Looking at the resonant frequency of hydrogen is not something that's new. I think SETI tried this 50 years ago, and they had this idea that if the aliens, the extraterrestrials, were anything like us and thought anything like us, they would know the kinds of things that we know in physics. And one of the things they would know is that hydrogen is by far the element most abundant throughout the entire observable universe. And they would know things, because they know physics like we do, that it has a resonant frequency. It's around 1.42 gigahertz. Which is really not that hard to work with. I spent a lot of time, I spent a few years playing with 2.4 gigahertz, which has a quarter wavelength stub of about 1.2 inches. I'll tell you what inspired me to be able to work on microwave and stuff is many years ago, 30, probably even possibly even 40 years ago, when I was out at White Sands. I was talking to one of my friends that was an engineer for the government that worked in millimeter wavelength RF, and I don't know the exact words I said, of course, but the conversation went like this. I said, I don't know how to deal with this microwave stuff, UHF, up there in the gigahertz range. And he said, well, you know how to build an 80-meter antenna, right? An 80-meter dipole that's 120 feet long? I said, yeah. He said, so you can use like 120-foot tape, right, to measure things? I said, yeah. He said, well, can you use a 6-inch ruler? I said, well, yeah. He said, well, then you can work with microwave. And that, I guess, took the fear out of it. And he's right. Now, it's got its challenges, of course. But that actually gave me the confidence to get into it. It was still a number of years before I actually did get into 2.4 gigahertz, because that was one of the older Wi-Fi frequencies. I guess it's still used, but most of it's 5 gigahertz now. The highest any of my equipment will go is 3.2 gigahertz. Well, spectrum analyzers will go higher than that. But anyway, I don't want to get lost in this. What I've done out here, I'm going to show you where I'm started. Is I made a little dipole, not a little dipole, a little monopole, quarter wave, thereabouts. This is not critical length. And I've got it connected into the signal generator right here. And I'm transmitting at or about the resonant frequency of hydrogen of 1.42 gigahertz. And right now it's 0 dBm. I've had it down as low as minus 70, and I can still pick it up inside. And when I go inside, you'll see where I'm coming from with that. To make measurements, real measurements at these frequencies, you need some interesting equipment. This is one piece that's very valuable. It's a directional coupler. See right there? And it's good from 100 megahertz to 2 gigahertz. They come in all sizes. Here's another one. A couple more. This is a much cheaper one, but it gives me the same results. And here's another one. What you'll notice about, say, this type, this one and this one laying on the workbench are basically the same, because you put the signal in here, take it out here, and then you measure its forward power at one place, you measure its reflected power at another place, and then you do the calculations if you must have SWR. And you can measure the outputs here if you've got a spectrum analyzer. But if you don't have a spectrum analyzer, you can use these little diode detectors right here. See, this thing screws off. You measure the incident power, and then you measure the reflected power. See, this is the incident, that'd be the forward power, and this would be the reflected power. And then all you actually have to do then is do the ratio of the voltages, and you've got the SWR. So they're pretty cool. And I don't know what the price of them on eBay is now, there's no telling. But you'll see why I'm talking about this in a minute when you see the antenna I've built inside. It's I'm using a parabolic dish I've had for many years. I used to have it up on top of my tower where I could rotate it, and there was a program called Aircrack, so you could go around. This is 25 years ago or so, I guess, when the Wi-Fi stuff first started coming out at 2.4 gigahertz is what got me into it. And you could go around with this air crack and you could crack their whip. And I did a few times just to see if I could, just to prove that I could. I didn't steal any of their internet or anything else, but you can't do that. You can't do that anymore. Security is a whole lot better. Here's a nice little instrument to use. What I was going to tell you though is if you try to measure SWR on something like this, I gotta take it apart so you can see. See this little antenna right here? Right here. And you see this length of so-called coax? It's probably just probably audio cable, shielded audio cable. Well, if you measure with that much, I guess there's about, I don't know, must be 8 feet or more there. You get an SWR really pretty darn close, because the coax is close to 50 ohms. And there's just so much coax that if you want to measure an antenna, if you want to measure an antenna like this, you got to measure it like right there. You'd have to cut this off and put some connectors on that you can put back together and measure it, but it's close enough. When you measure, when you determine wavelength, you see things all the time where they have wavelength over 4 for a quarter wavelength, wavelength over 2 for a half wavelength. The wavelength depends on a few things. One, if it's in free space, which is air or vacuum for our purposes. Maybe if you're a really whiz-bang physicist, you might want to consider the difference between the speed of light, speed of electromagnetic wave propagation in air versus a vacuum. But for us, it's all the same, and it's 300 million meters per second. Now, it's actually 299 million something or another, but the difference between the two is so insignificant that 300 million works just perfect. And speaking of coax, I gotta go back to the coax thing. Years ago, for some odd reason, I got into the idea that I wanted to build a J-pole antenna. So I went and bought 100 feet of brand new high-end Belden RG58, and I built the J-pole, and I put it up on my roof and attached it to the air conditioner up there. And I went back down in the basement where I run that 100 feet of coax. I didn't cut any of it off. I didn't roll it up either. I know better than that. It was all stretched out. And when I measured the SWR, it was perfect. I said, wow, man, I am one good J-pole antenna builder. But somehow I just didn't quite buy it. And this was for 2 meters, 144 megahertz range. So, just finding that too hard to believe, I went back up and disconnected the cable at the antenna. So all I had was a 100-foot piece of coax running from my basement up to the antenna, and the SDRUno was 1-to-1. It was perfect. There's a lesson to be learned there. You can't measure. The higher the frequency, the closer you've got to be to your antenna. Now, you can make your coax some whole numbers, called integer whole number multiple of a half wavelength, and you will end up with pretty much the same phase at the end of your coax as you have right at your antenna. But, you know, whatever. And I actually do that. I cut my 20 meter, since I use a monoband antenna on 20 meters, I do cut my coax to that wavelength. Now, there's where a quarter wavelength and a half wavelength are very different from free space or vacuum. Just call it free space, air and vacuum wavelength. Because you determine a quarter wavelength or a half wavelength of, for example, coax by knowing its velocity factor. So the fastest electromagnetic energy propagates is in free space, and everything else it goes slower. Everything. So if you're using old coax, it's usually about 0.66 or 66%. So if it's 10 meters exactly, the wavelength in free space, then the 6.6 meters of coax is a wavelength. I don't want to get onto this too much, but I want you to know that. The new coax, like say LMR 400, which is by far my favorite, there's one called LMR 400DB, which is rated for 20 years out in the sun or buried. Well, 20 years is, I'm sure, a whole lot more time than I got left, but its velocity factor, I think, is 0.8, 80%. So, an exact wavelength in free space of, say, 10 meters would be 8 meters of coax of LMR 400 if its velocity factor is 0.8 or 80%, however you want to state that. Hope that makes sense. And it's one of those things you got to know. Okay, well anyway, I think I've babbled enough out here. Let's go in. I want to show you the things that you need to build these UHF microwave type antennas. Here's one thing you need a big supply of. I'm going to try not to make a big mess, but you need lots of this little tiny tubing. Look at this stuff. See, like this kind of tubing right here. It comes in aluminum, brass, and copper. And you can buy this stuff to where it telescopes inside each other. So you can make telescoping antennas. Is that the right one? No. Yeah, well, that's not exactly the right size, but you can see how they can telescope together. And you can make adjustable length antennas with it. Really good stuff. But you gotta have a bucket full of that on every practical side. I get all this stuff at Hobby Lobby. See, like here's some. You know, see, this is I think 1/4 inch. If you use 3/4 inch water pipe, which is a 3/4 inch inner diameter, you need to use the inner conductor can be made out of brass or copper. You need it out of brass or copper so you can solder to it, but it needs to be 5/16 of an inch, because when you figure out the impedance of coax, it's 138 times the log of the diameter ratios. So if you do the diameter ratio of 3/4 to 5/16, and you take the log of that, base 10, you multiply it times 138, I think you get about 54 ohms. So there you go. Those are a few of the tricks for building antennas. This little thing right here is jewel. I like this. But sometimes you got to get serious, and you got to deal with you know, the real deal like this. So here's the it says use above a gigahertz, and I get 54.4 millivolts at 0 dBm at 2.4 gigahertz. And you have to move this one around. So you might say, well, why don't you just get two of them? Well, no two of them are going to be exactly alike. So you just got to move it around. You have to move it around from the input to the output, and that's how you get these voltage ratios. So there's a little bit of work involved in it, manual work. I think that's all that I wanted to show you out here. You've got to have a lot of parts. You've got to have a boatload of connectors, adapters, what have you. As you'll see right here, all these little short, open, and 50 ohm lobes to calibrate things. You've got to have all kinds of N connectors, N and SMA barrel connectors, whatever. Termination loads, terminating loads, and then there's another one right here. Let me show you this one. This is a nice one to pick up if you can find one. It's got all of the connectors to connect just about everything to everything. At least a couple of them. I'm not very good at looking with one hand. Sorry. See how this thing works? If you want the TNC, you pull it out, and then you put one of these things in, and then you want to convert it to a BNC right there, UHF, N, etc. PL259, SO239, SMA. That's come in really handy a lot of times. But you got to have a lot of that kind of stuff because you're always needing to convert something to something else. So let's go inside, and I'll show you what's going on in there. You might be interested. Okay, what I have in my den right now is my 4-foot parabolic dish, where I have built a 1.4 gigahertz dipole right here. This PVC tubing is just there for support, and I can loosen it up here in the back with this stainless steel clamp right here, and I can move it in and out to get the best focus, and I can turn it for horizontal or vertical polarization. I have a little low noise amplifier on right here that's actually quite good. I've had these things for years. I got this stuff back in the, like I say, the 2.4 gigahertz projects I was in long ago. Let's see, here's a couple that I was testing right here. Here's some of the cheapies, and here's another one. I thought, well, you never know, you got to test them all to see. But this one worked out very, very much better because see my right here, the good one right here gives me an output of minus 41 dBm, and the amp 2 was minus 60, so it's 20 dB less. These are pieces of junk. You know, the less negative this is, the more positive it is. I mean, the more powerful it is. Yeah, less negative. See, this is 20 dB less, and this one's 58, the third one. So this one, which obviously certainly looks like the better one, really is. Okay, so it's coming out, it's going into the amplifier. Now the only other thing I need, and I'm trying to decide whether to buy it or build it, is a bandpass filter, because that'll lower my noise floor. See, my noise floor right now is about, it's close to a minus 100 dBm. This is the signal we're transmitting from the workshop that I just showed you the little antenna connected to. And it's up at minus 40 dBm. If we want to look at the exact resonant frequency of the hydrogen, it would be, well, see, that took it off the scale. But I've got to zoom out to bring it back in, or zoom in. I don't know. This is not really important right now, but you can zoom in and out. There it is right there. Have to zoom in, you know, to get the bandwidth of what we're looking at here about right. Okay, so we can pick up, it goes to prove that the antenna's right. The transmitter's right, the frequency's right. Just absolutely amazing the accuracy of these instruments that we can have in wouldn't work something nowadays. And here's a beautiful spectrum analyzer. This one takes the RF in directly, straight from the antenna with a piece of wire, piece of coax, straight from here, straight to the antenna. Well, actually, I'd still put the low noise amplifier on it. But what I'm running it into right now is a thing called SDRPlay. It's a software-defined radio, and real popular. It runs this software right here. It's called SDRUno, and ham radio operators use it, including myself, of course. And you know, you can see the whole spectrum. Like if you want to look at 20 meters, you just go right up here to the 20 and click on it. See, now we're looking at the 20 meter band. Of course, we're not going to see anything because we don't have an antenna up. It put us at 14.175 megahertz. And then you can put over here in these boxes, whatever frequencies you want to go to. There's the exact resonant frequency of hydrogen, which is where the red line is, and this is where we're transmitting this for a marker. 14.2. See, if I put it on 14.2, you'll see it moved over right in there, and it's full quieting. So you don't hear any hissing. Look how strong the signal is, actually. Where's that red line? Right there. You know, see, it's almost pegged out. It's at minus 39.9 dBm down here. But that's very, very strong. And you've got RF gain over here. Right here. You've got the RF gain down really low. I can crank it up. You can see it's so strong it overloads. I made some little clip-it videos a little earlier of this antenna. I get just over 20 dB gain out of it. So the antenna is actually working quite well. And it's the same kind of numbers I've gotten off of it multiple times. I think I get something like 25 to or better dB gain at 2.4 gigahertz because, you know, the antenna is bigger for that wavelength. And there's my kitty cat right there. I'll call her Angel. So what are we going to do with all this? Well, like I say, I've been inspired by my friends to, when we went camping up at Aguirre Springs, we like to think about the aliens. I mean, we're right above White Sands Missile Range. If you were an alien, wouldn't you want to land right next to White Sands Missile Range? You can actually see the headquarters of it from the Aguirre Springs camping site. But one suggestion is to be able to hear it. Now you can go on YouTube and you can find all kinds of stuff where people will show you how they have found and can display the resonant frequency of hydrogen clouds. In particular, if you're looking through the plane of the galaxy and at different places in there, depending on the how directive your antenna is, you can pick up different amplitudes of hydrogen. So, I got a kitty cat going to walk up on my keyboard. Having a kitty cat walk on your keyboard is a bad idea because they can do things to it that you don't know how to, that you've never imagined. But she's a jewel. Anyway, and here's the beautiful spectrum analyzer. Well, anyhow, this is it. Hope it inspires others to get into a little bit of radio astronomy. I guess this is kind of like a first step. So I got more amplifiers over here. This is a really powerful one. This one goes from 1 megahertz to a gigahertz, but it works at 1.4 also, and it puts out 1 watt, so it's pretty powerful. I was using it earlier, but the one that I was using it for the amplifier, but this one right here works just as good, and it's a lot smaller, little SMA connectors, etc. See the way this thing plugs in, it's self-powered by the USB, the old style USB connector, straight into the computer over here. And here's some more antennas, little monopole antennas. By the way, I tried to use these USB cable extenders, and not a single one of them will work anymore. And they're not all bad. There's 3 of them there. They're not all bad, but they don't work. maybe you guys that know more about PCs and stuff nowadays can tell us why they don't work anymore. And of course, like I say, you got to have wheelbarrows full of all kinds of adapters and connectors, SMA in, mostly SMA and in, dummy loads sometimes. Here's a cute little, could measure the SWR with this one to 1.5 gigahertz. Yeah, she's got to check it out here. Kitty Cat's got to check it out. Well, anyway, that is what I will start with. I can't think of anything else at the moment, but I hope it inspires some of you. I hope some of you guys know something about this and can share what you know about it. If you've done any radio astronomy, especially in the 1.4 gigahertz range, please share all you know. There's a lot on the internet, but I've had to look pretty deep to find all this stuff. Last thing I might say here is these are some of the older things that a lot of guys on the internet use, these RTL SDR, because they're quite inexpensive, and they go up to I don't know, a couple of gigahertz. I don't remember exactly, but anyway, this little SDRPlay goes up to 2 gigahertz, and it has sound. I think I mentioned that. I don't know if I expounded on it quite enough, but we want to hear it. We want to hear to the left and to the right, right in the middle. We don't want to just see it. We don't want just a graphical display. We want to be able to hear the sounds of the moon, if there's any hydrogen spectra that's going to excite our antenna up there. Surely the sun will, and then the galactic clouds and whatever. Well, I won't hook all of this stuff up to something else and show you, but the spectrum analyzer does just as good a job. But it's really pretty amazing nowadays, the equipment we can have, just as I've already mentioned. And this thing right here is practically a receiver. Of course, it takes a computer to go with it. But it replaces this magnificent piece of equipment right here, which I love this thing. But anyway, there you go. Stay safe, my friends, and constructive criticism. That's not the word. Constructive comments and information is always appreciated. Thanks a lot.